So today we'll be graphing inverse functions. The idea is that we're graphing a reflection over this diagonal line y equals x, because if we remember in inverse, what we've done is we swap the y and the x, and this is our key point right here as to what an inverse function is. We said we swap the x and y variable. That's because it's a reflection across the x equals y axis. This is going to give us a relationship on what we're going to visually see here. Now there's a couple ways that we can do it. We're going to start out with the algebraic method that we're already familiar with, where I'm going to turn this into a y and say this is 3x minus 2. And we're going to go ahead and we're going to solve for the variable x. Now we've discussed previously that we could swap the x and the y and resolve for y, but again, I think that kind of undermines the importance of what we're doing here, where we're actually just solving for the x. We're seeing the graph from the other perspective. So we're going to go through and I think we've got this. So we're going to add a 2 to both sides. So we're going to say that is going to be a y plus 2 is equal to 3x. Then we're going to divide both sides by 3. Now when I divide both this by 3, I'll get a 1/3 y, because that's whole y divided by 3, and a 2/3. And that's going to be equal to my x. Now this right here is my inverse function. If I wanted to write it in function notation, what I'm going to do is I'm going to say this is f prime of x, my inverse function, is equal to 1/3 x plus 2/3. And now this is where we actually rewrite this with the swapped x and y values. Our original function up here, we see the fact that the only difference is the f and the f prime. This says, hey, we have our original function. This is, hey, this is our inverse function. Actually, it's not f prime, it's f negative 1. So strike that. F negative 1 of x. That's going to show that's our inverse. F prime is actually the derivative, of which we haven't learned that just yet. And so our end goal today is going to be to graph this thing. So let's go ahead and before we deal with this right here, let's see what our table of values would look like if I gave ourselves an f and f of x in this. Let's plug in some values. Let's say -3 to 3. It's a nice good variety of different values there. So if I plug these in, I'm going to multiply it by 3 and then take away 2. So -3 times 3 becomes -9. Take away 2 is -11. Triple -2 becomes -6. Take away 2 is -8. -3 minus 2 is -5. 0 minus 2 is -2. 1, 2 minus 2, or 2 times 3 is 6, minus 2 is 4. 9 minus 2 is 7. So we have a nice little variety of values. Now, if we were to do the inverse of x, this f negative 1 of x, we would need to create an entire new table. So f negative 1 of x. Boom. So we got that. Now what I could do is I could pick a series of arbitrary points, but bear with me here for just a moment. I'm going to pick 2 completely arbitrary numbers, and I'm going to plug them in, and let's see if we can't spot something that's going on. I'm going to plug in the value of -2 and 1. They're within our range of -3 to 3, but I'm just going to plug in the -2 and a +1. I'm not going to plug in all of these different points. I just want to plug in those particular 2. Now, let's see if we can't figure out what happens. Now, if I plug in a -2, -2 times a third is -2/3, plus 2/3, I get 0. And if I plug in a 1, 1 times a third is 1/3, plus 2/3 is 3/3, and 3/3 is going to be equivalent to 1. Don't know if we spotted it just yet, but let's go ahead and see if we can't figure out a little more. So if we notice we go up by 1, this is a line. So for every up in 1, I have to go up in 3. So if I wanted my next point to be at a 2, I'd have to go up by 3 to 4. Let's double check to make sure that logic holds true. If I plugged in 4, that becomes 4/3 plus 2/3 is 6/3, which is 2. Perfect. And so again, if I wanted to go up by 1, I'd have to go up by 3. Let's plug in that 7. So 7/3 plus 2 is 9/3. 9/3 is 3. Have you spotted it yet? So what we notice goes back to this relationship. X and Y. What do we do in the original equation? We solve for the other one. What was one of the ways that you can solve for an inverse? By swapping the X and the Y. Let's take a look at these values. I have an X of 0 and a Y of -2. Right here I have an X of -2 and a Y of 0. It looks like they've swapped. And in fact, each point as we go down our table, it looks like we've just swapped the X and the Y. So swap X and Y. So if I want to create a table for my inverse function, I don't actually need to plug in a single thing. I can just look at my Y and plug that in as my X, look at my X and plug that in as my Y. And I know that any point on here, if I plug in a -11, it's a -11/3, plus 2/3 is -9/3, which is -3. I know that every single one of these points will hold true to that pattern. So we literally just swap our X and our Y. And so graphing it, let's see what this visually looks like. We understand that the process mathematically is familiar. We now see that the table is going to have a very distinctive and very easy method to solve. Now let's see if we can't see what's going on with the graph. So I need to go from -3 to 3, or from -11 to 7. So this is pretty balanced. We're going to go ahead and we're going to put the axis right here in the center. And again, because I'm dealing with the X and the Y's and then I'm swapping them, I know that I'm going to have to put the Y-axis in the center as well. And because that limits me to a 5 by 5 in each quadrant, and I need to get to an 11, I'm going to do the X by 2's and the Y by 2's. And in essence, what I'm just going to skip this point. That 11 kind of throws everything off. Everything else fits within the 1-to-10 ratio. So I'm not going to graph that point, but I'm going to graph everything else. So let's go ahead, and first off, we're going to graph a reflection over the diagonal line of y equals x. So we want to graph the line of reflection, which means that we're going to have to take a diagonal line, perfectly diagonal line, and graph it along the entirety of the graph. And so there's my line, y equals x, and everything is going to be reflected over this point. So let's see if we can't spot this. So -2, -8, 2, 4, 6, 8, -1, -5, 2, 4, 5, 0, -2, 1, 1, 2, 4, 3, 7. Perfect. We have a very straight looking diagonal line here. So we graphed our points well. So if I take that and I say, cool, this is our f of x, we know that across this line, we should have a direct reflection, which means that any point on one side is going to be reflected directly to the other. So at what point do we automatically know when I reflect it to the other is going to be on both graphs? That point right there, which I believe we said was at 1, 1. And we notice that each graph has a point of 1, 1 within it. So every inverse function is always going to contain at least one point as long as it touches the axis that it shares with its inverse. Even if all their points don't work, if it touches the line of reflection, it will share at least one point with its inverse. And so now let's see. 2, 4, 6, 8, 2, 2, 4, 5, 1, 0, 1, 1, perfect. 4, 2, 6, 7, and 3. And what we notice is that, again, our math is good because we have a perfect diagonal line that's going on right here, and this is our f inverse of x. And so if we look at this graph across the line of reflection, what we see is that each point, if I take it, and let's do this in, I've already got a green. Let's do this in purple. What we notice is that theoretically, if I were to be able to do this perfectly diagonal, let's use the 2 points right there and right there at the corners of the axis. The distance on the left of the line should be equal to the distance on the right of the line. And so, boom, we notice that both sides, if I do to the left, is that a diagonal? Yeah, that's a diagonal. On the left and on the right, they're perfectly symmetrical. So again, we notice that both sides are equal all the way along. It's quite literally flipped over the line. Now, not necessarily intuitive to see it from this angle, but we notice the fact that there is a reflection going on. Some of you might assume that it's more of a twist. However you want to look at it, we're swapping the x and the y. So let's move on to another one. Now, albeit most of your inverse functions are going to look something like this if you're dealing with linear equations. They're going to touch the line at some point, whether it be way up here, way down here, it's going to cross at some point. But we have two different types of exceptions. And what we have is we have our first exception right here, where we have a slope of 1. And let's see how this will work out if we try and solve for our inverse. Well, I know I need to just subtract the 6, so I have y minus 6 is equal to x. And boom, there we go. So f negative 1 of x is x minus 6. And here is our inverted function from the original. We know that if we create a table for the original function, so f of x, plug in some values, let's say negative 3, negative 2, negative 1, 0, 1, 2, 3. I'm going to plug those in. So negative 3 plus 6 is 3, 4, 5, 6, 7, 8, and 9. All we need to do to get to our new function over here, so f negative 1 of x, is we just swap the x and the y. So 3, negative 3, 4, negative 2, 5, negative 1, 6, 0, 7, 1, 8, 2, 9, 3. So we're going to swap. That's all we do. And so graphing it, let's take a look. This time, we're dealing with all positives and then negative 3 to 9. So I'm going to draw my axis right here, and I'm going to do it by 2s. Should be enough. And wherever I put the y-axis, I need to put the x-axis in the same orientation, in the same location. So my x is by 2s. My y is also by 2s. Let's graph our diagonal line. Our diagonal line of y equals x, right there. Now, you may have already noticed at this point, both our original function and our inverse function contain the same slope, with different y-intercepts, which by definition, if we remember from the geometry concept, they are parallel lines. So how many times will they actually touch our line of reflection? 0. So we know that if they touch the line of reflection, they're going to share a single point. These aren't going to share any points. So let's see what we can do. So 2, 3, 2, 3. We know that every one of these points is along this diagonal. And it makes sense that they're going to be parallel lines because if we reflect it entirely across there, we know we're going to get a line that looks roughly like this. And so if we actually graph these points, 3, -3, we do. And that's exactly what we expected. We expected to see every point on here completely reflected onto the other side. And that is exactly what we got. Boom. So that was the first exception that you might get. Another exception that you might get would be something like this. Now with this, I have a slope of -1. So it's a different slope. What's the big deal about it? Well, let's try it out. So our first idea is to subtract the 5. So y minus 5 is -x. And then we'll divide everything by -1, and that will change the sign on our x. So we'll have a -y plus 5 is a positive x. And we're going to take that and we're going to write our inverse function of -x plus 5. And if we paid attention to the last one, we noticed that they had the same slope, but they had different y-intercepts, which meant they're parallel lines. These have the same slope and the same y-intercept, which means these are going to end up being the same line. And, well, why is that the case? Well, let's build a couple values just to make sure that that's going to be the case. So x, f of x, -3, -2, -1, 0, 1, 2, 3. Change the sign and add 5. So 8, 7, 6, 5, 4, 3, 2. And if I swap the x and y going over, we're going to get a new function, f, or x. F inverse of x is going to give us 8, 7, 6, 5, 4, 3, 2. -3, -2, -1, 0, 1, 2, 3. We notice 3, 2, 3 2s on there, 2, 3, and 2, 3. So I've got at least 2 points, and if it's a straight line, I know the rest of these points would be on there as well. In fact, if I went down to 1, that would be going up to 4. If I went down to 0, that'd be going up to 5. In fact, we can work our way all the way up the table. But let's take a look at this. So I have -3 to 3, and I've got all the way up to 8. So we're going to stick with our same location as our last one. We're going to plug our y-axis here and our x-axis in the same spot. It's by 2's, and our y is by 2's as well. Perfect. So -3, 2, 4, 6, 8, 7, 6, 5, 4, 3, 2. Let me stop there. Oh, we forgot to draw our line of reflection. And so if we notice that all the points on the left are leading directly to the line, which means if we reflect them, it's going to keep going. And that makes sense because if we remember, these both have the same slope. The slope of my line right here, if I read that as y equals mx plus b, the slope of my reflection lines, let's call it the slope of r, is a +1. I'm actually going to do that as a fraction, so +1 over 1. And the slope of my inverse, let's call that m of I, is -1 over 1. And if we look at these two values, we notice that these are what we call negative reciprocals. Which should ring a bell in your head. Whenever we have a negative reciprocal slope, the lines are perpendicular, which means that they're going to cross at exactly 90 degrees. So if I have a line that does this, and I'm going to call this my f of x, then this line also is going to intersect at the same angle. In fact, we could check with our previous example. We could measure the angle from the line. A different way to measure it is the angle between the line of reflection and our angle is equal to the angle of the line of reflection and the new line. So we have two congruent angles right there. So we would also have two congruent angles on our new graph. 2, 4, 6, 8, 2, 2, 2, right there. And so all the points are right along here. 2, 3. And so our new line is right on top of the old line. Perfect. And so the last one that we want to do is what happens, and we're going to be exploring this a little further when we cover radicals, but what happens with an inverse of a quadratic? So I want you to pause the video, give it a shot, and see if you can come up with what the inverse function of a quadratic is. And I'm going to leave you with a little hint. Make sure that your inverse is, in fact, a function, which means that for every x you plug in, you should get one answer. Pause it, give it a shot, resume it when you're done, and see how you did. Okay, let's take a look. So we know that we're going to swap our variables. We know I'm going to end up solving for x right here, which means I'm going to have to subtract 4. So y minus 4 is x squared. And then I'm going to take the square root of both sides. And we remember that when we artificially put in a square root, we get plus or minus, which means that our f negative 1 of x is a, hold on, positive and negative of y minus 4. So if I plug in an answer, I'll get, or if I plug in an x, I'll get 2 results. And that is an x, because when we write it in function notation, we actually do write that with an x. And what you may have realized is that this is not a function, because of that right there. But what, okay, so what does that mean? Well, let's build a table and see exactly what that means as far as plugging in our values. So if I build a table with x, f of x from negative 3 to 3, I square the number and add 4. So 9 plus 4 is 13. It's going to give us 4 plus 4 is 8, not 7. Negative 1 squared is 1 plus 4 is 5. 4, 5, 8, 13. What we notice is the fact that our y values are repeating, which isn't a big deal for this function because the y's can repeat all day, every day. We don't care. The x can't. So we know that when we swap, that's going to present a problem with these values or with these values. So what you could do is you could actually make this one or the other. You could say, hey, I can make this into a function if I only use part of the graph. So how about I only use the positive, or I only use the negative? So I have one option where I say, okay, so 13, 8, 5, 4, 5, 8, 13. Negative 3, negative 2, negative 1, 0, 1, 2, 3. So we have option 1, where I plug in all the numbers and I only take the positive result. So function if I only take the positive, or I could only take the negative result, which leaves me with this. This is also a function. I can't do both of them. What does that look like? Well, looks like we're dealing with -3 to 3 and a bunch of positive numbers, so let's put the graph right where we've had it. So the x by 2's, that seems to be the trend here, and the y by 2's. And we're going to graph our line of reflection first. And our original function. -3, 4, 6, 13, 12, 10, 8, 6, 5, 4, 5, 8, 13. And we notice that the graph that we end up making is a quadratic, so it has a curve, which really for the inverse, we don't really care too much, so our f of x. That means that we're going to have to reflect this curve over there. So we're going to have the general shape if I reflect it. Let's see. Something like that. And we know that this wouldn't actually pass the vertical line test. If I ran a vertical line across it, I would touch twice, twice, twice. I could get around that by saying, well, how about I only take the top half? If I only looked at the top half once, it's perfectly fine. Or I could look at the bottom half and say once. That'd be perfectly fine. So we see that's exactly what we've said. If I only take part of this function, I'll be fine. But if I take both of them, we have problems. So what you're left with is you're left with a choice. You can either take the 2, 4, 6, 8, 10, 12, 13. You can either take the positive values, so 3, 12, 10, 8, 2, 6, 5, 1. You can either take the positive values right here, which would only be that part of the function inverted, or what you could do is you could take the other part. You could take this right here. You could take the top or the bottom, but not both. And we'll learn later on that is one of the big things. If I take the positive value, that's going to be a radical function. We're going to cover those in a later video. And so the last question I leave you with is something that you'll probably see at some point on either ACT, SAT, some sort of state test, district exam. This is a very popular question. What limit does y have in order for the inverse to still be a function? We just saw a piece of that. If I want the inverse to be a function, I had to take a chunk or a chunk. I couldn't take the whole thing. So how about if we're given this scenario, what could y not be? So if a function is allowed to have an x with a repeating y, but I can't repeat the x value, I'm going to look at my x values. 2, 3, -1, well, 2. So I know that this right here, the original, so f of x is not a function because I repeated one of these. I don't care if I repeated the y or not. I can't repeat an x. So my original is not a function, but I don't really care about the original. I want to know what y can or cannot have in order for the inverse to be a function. So I'm going to pay attention to the other variable. Let's see, I have a 4, an 8, and a 1. As long as I don't repeat one of those, if y was, let's say, a 6, or 2, or 1/2, or in fact, if y was anything that is not a 1, a 4, and an 8, we would be good. And so there's our answer. As long as y is not one of those three numbers, the inverse is a function, even though the original was not. And there you go.